All right, welcome back. We just discussed R3, which was polynomials. One thing I'll just point out on my website is if you go down here to County College of Morris, math, and then scroll down a little bit, you could already see that I posted some stuff. If you take a look at the factoring review, so I always say that the most important thing in math is factoring. And you really need to make sure that you're strong on that. Eventually, we're going to be factoring polynomials, but we are also going to be factoring trigonometric expressions. So you want to make sure you're good with the basics. I have the formulas at the upper right over there, but if you can't do these, we're going to have a problem. So this is a prerequisite for this class, that you could factor trinomials, special cases, using GCFs, and the last one would be a factor by grouping problem. Perhaps we could talk more about this on Thursday, but I would like everyone to take a look at this worksheet. The answers are posted on my website, so you could actually see step-by-step how to do this. And that's what I'm going to do going forward. Oops, clicked on the wrong thing. Now it's yelling at me here. Yeah, let's go back out. Sorry about this here. Let's try to go back to my wiki. And like I tried to do before, we're going to go back and just click on the review solutions right there. And click on download. So you can see this is the same paper we did. I just took a picture and I showed you step by step how to do these. So please take a look at that, and we could talk more when we see each other in person. So as far as our next topic, it's going to be section R5, and R5 is rational expressions. I'll write that down up here, R5, rational expressions. All right, and with rational expressions, what a rational expression is, rational, if you remember, was a type of number that could be written as a fraction. So generally we have a top part, the numerator, and a denominator. And one of the first things that you'd be asked to do when we're dealing with rational expressions is find the domain. And what the domain is, domain just means the possible x values. So if we're dealing with a fraction, the way that we do this is we set the denominator equal to 0 and solve. Let me show you an example. We had an example like this where it was 3x minus 1 times x plus 1, all divided by x plus 2 times x minus 5. The directions were to find the domain, we set the denominator is equal to 0. So the denominator is this right here. So what we would do is we'd say x plus 2 times x minus 5 is 0. And if we have two expressions that when we multiply we get 0, that means either x plus 2 is 0, so x is negative 2, or x minus 5 is 0. So x would be 5. Those are numbers that can't happen. So we can't have, if x is negative 2, our denominator is going to be 0, and that's a problem. So the way that we write this in set notation is we say all x values are in the domain such that x cannot equal negative 2 or 5. That's one way to write it. Depending on who your teacher is, we could also use interval notation. So interval notation would be from negative infinity to negative 2. What we're trying to do is we're trying to tell what the domain is. So you could plug in any number you want from negative infinity to negative 2. You can't use negative 2, so we use an open parentheses. From negative 2 to 5, not including those numbers, and then from 5 to infinity. Either of these notations is fine for me. Okay. Next is to write a rational expression in lowest terms. And really, one way to think about this is to factor and cancel common factors. So we talked a little bit in the beginning about factoring. Factoring is really important. We're looking to take out the GCF from the numerator and the denominator, and then see if we can cancel from there. So let me show you an example. The directions would be to simplify (2x plus 8) divided by 2. So the GCF from the numerator would be 2, so we could go ahead and factor that out. The GCF from the denominator is 2. So if we cancel out, because we're multiplying by 2 and dividing by 2, it's like taking 2 steps forward and 2 steps back. They cancel out. If we cancel these out, our answer would just be x plus 4. Similarly, if we had a problem like this, 2x squared plus 7x minus 4 divided by 5x squared plus 20x, what we want to try to do is look to see if we could factor using GCF factoring. And it doesn't look like that's going to work. So generally when we're factoring, I follow these steps. Step number 1 is we take out a GCF. So that would be like the bottom. The bottom, we could totally take out a 5x, and we're left with x plus 4. But there's no GCF on top. Next step we try to do is we try to factor by grouping. Grouping would be like if you had 4 terms, and you cut it down the middle, and you factored out a GCF from the first half and the second half. We'll see that in an example in a little bit. The third thing we want to try to do is factor trinomials. Some of you might have heard of the AC method, which is what's going to happen with the top here. So with our numerator, we have 2x squared plus 7x minus 4. Generally what we could do is we can make like an x like this. And we could say 2 times negative 4. So if this is a and this is c, what we would do is we'd say a times c. 2 times negative 4 is negative 8. The bottom would be 7. So we have to try to find 2 numbers that multiply to be negative 8 and add up to be 7. So negative 8 and positive 1 would get the job done. So next what we could do is instead of writing 7x, we could write negative 8x plus 1x minus 4, because these 2 terms, essentially let me see, did I do this wrong? They have to multiply to be negative 8, add up to be 7. So this should be positive 8 and negative 1. Sorry about that. So 8x minus 1x would be 7x, which is the same thing we started with, but we're just changing the form. If we cut it down the middle now, we could do what's called factor by grouping. The first half we could take out a 2x, and we're left with x plus 4. The second half we could take out a negative 1, we're left with x plus 4. So really we have an x plus 4 in common across the board, and we have 2x minus 1 left over. So I'm going to go ahead and put that up top here. X plus 4 times 2x minus 1. To finish up this problem, we could cancel out our common factors. So the x plus 4's would cancel, and your final answer for letter B would be 2x minus 1 over 5x. And then our last question in this topic would be if we had x squared minus 2x plus 1 over x squared minus 1. Now the top, it's a trinomial. So the way that we factored trinomials is we made our x, and we said, what's a times c? 1. That add up to -2. We could use -1 and -1. So we get x squared minus x plus 1. We're just changing the form of this. Cut it down the middle, we could take out an x, and we get x minus 1. Take out a -1, we get x minus 1. You know you factored correctly if you get GCFs. So the top would just turn into x minus 1 times x minus 1. Now the bottom isn't a trinomial, it's not 3 terms. So the very last step that we try to do for factoring is we look at special cases. Special cases would be if we had a difference of squares. The formula looks like this. Or if we had a sum or difference of cubes. So this is from Algebra 2. What we would do is we would keep the same sign. Then we do a squared, the opposite sign, ab, and then always positive b squared. Sometimes when I talk about this, I use the acronym SOAP, meaning same sign, opposite, and then always positive. X squared minus 1, let's just put this over here. This is the numerator. This is how we factored x squared minus 2x plus 1. But if we're taking a look at the bottom, it's not a trinomial. So you could put 0x there, but this is a special case. So x squared minus 1 is the same thing as x squared minus 1 squared, which according to the formula is x plus 1 times x minus 1. We could cancel out our common factors, leaving our answer x minus 1 over x plus 1. Please make sure you take a look at that factoring sheet. If you don't know how to factor, this is going to be a difficult time for you. All right, we have 2 more topics to talk about here under rational expressions. One is how to multiply and divide, and then another one is how to add and subtract. So let's do one at a time here. Let's take a look at how to multiply and divide. And generally when we're multiplying, so let me just show you an example. When we multiply fractions, which is really what a rational expression is, when we multiply, we just go straight across the top and straight across the bottom. So if I asked you what's 1/2 times 3/5, the answer is 3 over 10. The only time we get a common denominator is when we add or subtract, but that's going to come up in a little bit. When we divide rational expressions, we multiply by the reciprocal. We heard that word before, reciprocal. What that means is we switch the top and bottom of the second fraction. So if I asked you to do an example like 1/2 divided by 3/5, we keep the first expression the same, we change division to multiplication, and then we flip 3 over 5. That's the reciprocal. 3 over 5 and 5/3 are reciprocals. So keep, change, flip, and if we multiply straight across, the answer would be 5 over 6. So let's take a look at a few examples where we're multiplying and dividing. Say if we had 2y squared over 9 times 27 over 8y to the 5th. There's a few things we could do. We could look to cross reduce, Generally what I do is I just deal with everything at the end, meaning I just multiply straight across. 2 times 27 is 54. And then 9 times 8 is 72. At this point, I would try to reduce this as much as it could be. So 54 over 72 is the same thing as 3/4. And we saw this property before. Y to the second divided by y to the fifth is y to the negative third. But we don't want negative exponents, so we could put this over 1 and then just bring this to the bottom. So we get 3 over 4y to the third. That would be our final answer. All right, so what about if we had one a little bit more difficult with polynomials? So if we had, let's say, 3p squared plus 11p minus 4, all divided by 24p to the third minus 8p squared, divided by 9p plus 36, all over 24p to the fourth minus 36p to the third. All right, so obviously there's a lot going on here. First thing I would try to do is I would try to factor everything, and then division turns into multiplying by the reciprocal. I'll show you how this all factors. The top, so when we have 3p squared plus 11p minus 4, I'm going to use my AC method. We could multiply to get 12, 3 times negative 4, and they have to add up to be 11. So at this point, so we could use 12 and negative 1. We would factor by grouping. 3p squared plus 12p minus 1p minus 4. Cut it down the middle, take out a 3p, get p plus 4. If we take out a negative 1, we get the same thing. If this term is negative, we have to remember to take out a negative. So we wind up with p plus 4 times 3p minus 1. That's what the top factors down to. We'll deal with that in a little bit. Right underneath that, the denominator, 24p to the third minus 8p squared, I want to look to factor. And when we factor, remember that list we made? When we're factoring, we try to take out the GCF, then group, then trinomials, and then if all else fails, we go to special cases. So in this case, we could take out an 8p to the second, and we're left with 3p minus 1. So you have that first fraction totally factored. The second fraction, we have 9p plus 36. We can take out a 9. We're left with p plus 4. And then on the bottom, we have 24p to the fourth minus 36p to the third. We could take out a 12p to the third, and we're left with 2p minus 3. All right, so let's tie this all together. Completely factored now, we have p plus 4 times 3p minus 1 over 8p squared times 3p minus 1. That's the first fraction. To save a little bit of time, I'm not going to write divided because we talked about this before. We know that division is multiplying by the reciprocal. So 9p plus 36, I'm going to write that on the bottom. This would just be 9 times p plus 4. And then 24p to the fourth, we said that this was 12p to the third times 2p minus 3. When we're multiplying, we go straight across. So this is going to be 12p to the third times p plus 4, 3p minus 1 times 2p minus 3, all over the bottom. 8 times 9 is 72. P to the second times 3p minus 1 times p plus 4. If we multiply by the same thing we're dividing by, we could cancel those out. So the p plus 4's cancel. 3p minus 1's cancel, and what we're left with is 12 over 72, which reduces to 1/6. P to the third divided by p to the second is just p to the first. And it looks like we still have a 2p minus 3 left over. So really, this would be a totally acceptable answer for me. This would be fine. Sometimes in your book, you might actually see them put this over 1, and you might get like p times 2p minus 3 all over 6. But either of these answers is totally acceptable for me. All right, you should be able to recognize what's the same thing. One more example with this, and then we'll go to adding and subtracting, would be, am I on C? Yep. C would be x to the third minus y to the third, which looks like a special case, difference of perfect cubes, over x squared minus y squared, difference of perfect squares, times 2x plus 2y plus xz plus yz. That's 4 terms. So as far as factoring, we could look to take out a GCF, but generally when we see 4 terms, we want to factor by grouping. Over 2x squared plus 2y squared plus zx squared plus zy squared. Just like before, we're going to factor first, and then we're going to look to cancel out common factors. So if we take the x to the third minus y to the third, that's a difference of perfect squares. We have our difference of perfect cubes. And according to the formula, we write the same thing, x minus y, times the first term squared, opposite sign, xy, always positive, second term squared. That's how the upper left numerator factors. Next we have x squared minus y squared. Well, this is a very typical difference of squares problem. We could factor this as x plus y times x minus y. That's the denominator. But then we have these complicated terms here. We get 2x plus 2y plus xz plus yz. 4 terms. We try to cut it down the middle and factor out a GCF. We take out a z in the second group. And you could see we factored this correctly because we do have the same factors here. So this would be x plus y times 2 plus z. Or z plus 2, it's the same thing. I'm going to try to factor the denominator, and then we'll put it all together. So we get 2x squared plus 2y squared plus zx squared plus zy squared. We cut it down the middle, take out a 2. We, of course, get x squared plus y squared. We could take out a z, and we're left with x squared plus y squared, which means we factored correctly. We got the same thing here. So we would get x squared plus y squared, which is the GCF of the whole thing, times 2 plus z. So now that everything's completely factored, let's try to tie it all together. We would get x minus y times x squared plus xy plus y squared over x plus y times x minus y times x plus y times 2 plus z over x squared plus y squared times 2 plus z. And if we're multiplying straight across, we can cancel out the x plus y's. We're eventually multiplying and dividing by the same thing. We can cancel out the 2 plus z's. We can take out the x minus y's. And really all we're left with is x squared plus xy plus y squared over x squared plus y squared. That would be our final answer. There's nothing else we could do with this. There's no such thing as a sum of perfect squares. There's no such thing here. So to finish up this section, what I wanted to do is talk about how to add and subtract these. So adding and subtracting rational expressions. So really, we're talking about how to add and subtract fractions. So what we want to do, the main thing, is we want to get a common denominator. As long as we get a common denominator, we could combine the fractions. So just like you probably saw, I'll show you some examples where we're simplifying, and then that'll be it for this section. If I asked you to simplify 1/2 plus 1/3, I think we learned how to do this maybe in first grade. The common denominator would be 6. So we have to try to make the 2 and the 3 into a 6. And the way that we could do that is by multiplying by a fancy form of 1. If we multiply this by 3 over 3, multiply this by 2 over 2, 2 over 2 is just 1. 3 over 3 is 1. We're just multiplying by 1, but we're changing the form because the LCD is 2 times 3, or 6. What we get is we get 3 over 6 plus 2 over 6 is 5 over 6. That would be our answer. So now let's take a look at, problems at this level. What if we had 5 over 9x squared plus 1 over 6x? The hardest part is figuring out what the common denominator is, and then we have to make our denominators into that. So just taking a look, if we had 9 and 6, I can make 9 and 6 both into 18. And there's nothing wrong with going a little bit bigger, like 9 times 6 would be 54. We would just have to simplify at the end. But 18 is the smallest number that both of them go into. The one on the left has x squared, the one on the right has x. We have to make both of them into x squared. So we could just very easily multiply the x by x. So 18x squared, it would be what we want our denominators to look like. So if we multiply the left by 2 over 2, that would get the job done. On the bottom, it would be 18x squared. On the right, if we multiply the 6 by 3 and the x by 1, so this would be 3x over 3x. So we get 10 over 18x squared plus 3x over 18x squared just turns into 3x plus 10 over 18x squared. And that's it. We look to simplify. There's no GCFs to cancel, so we're done with this. Sometimes it could get a little tricky, though, like if we had y over y minus 2 plus 8 over 2 minus y. The denominator, y minus 2 and 2 minus y, are almost the same thing. But they're not, right? And you don't want to do y minus 2 times 2 minus y. That's just a little complicated. So it's kind of like if we had the number 2 and negative 2. They're almost the same thing. They're off by a negative. Or 1 minus 2 and 2 minus 1. They're almost the same thing, but this would be negative 1, this would be 1. The trick that we could do is just factor out a negative 1. So watch how this works here. Oops. Sorry about that. What we could do is we could say this is y over y minus 2, and this is 8, but we could rewrite it negative y plus 2. Or we could factor out a negative 1 from that second fraction. I'm just going to plug in my computer here before I lose everything. So just be right back. Hold on. So the least common denominator right here, now that we see that the y minus 2's are there, looks like the least common denominator would be a negative 1 times y minus 2. So that's what all our denominators have to look like. So we just need to multiply this by negative 1 over negative 1. And we get negative y over negative y minus 2 plus 8 over negative y minus 2. If we combine them now, would be negative y plus 8 over negative y minus 2. We could simplify this if we take out a negative 1 from the top and bottom and just cancel them. This would really be the ideal answer. Completely simplified, there's nothing else to take out. All right, let's see what else we have here. So what if we had a problem like this? 3 over x minus 1 times x plus 2 minus 1 over x plus 3 times x minus 4. Your least common denominator has to have the same factors there. So this one has an x minus 1, so all of them need an x minus 1. This has an x plus 2, all of them need an x plus 2. X plus 3, x minus 4. So what we're going to do here is try to multiply by whatever we're missing. It looks like the fraction on the left we need to multiply by x plus 3 and x minus 4. The one on the right we need an x minus 1 and an x plus 2. So now our denominators are all the same, so we can combine the top. The whole denominator is just going to be x minus 1 times x plus 2 times x plus 3 times x minus 4. But on top we're going to have 3 times x plus 3 x minus 4 minus 1 times x minus 1 times x plus 2. So we have a little bit of work to simplify. This would be 3 times x squared minus x minus 12 minus x squared minus x minus 2. All right, let me see. This would be x squared plus x minus 2. We usually always leave the denominator completely factored, and we always try to simplify the top. So the top, let's see what this turns into. 3x squared minus 3x minus 36 minus x squared minus x plus 2 over the denominator. Let's simplify the top, see if it'll factor, and then we'll be done with this. So 2x squared minus 4x minus 34 over the denominator. It's a good thing I'm doing this on the computer, otherwise you might be tempted to throw something at me for taking so long here. We could take out a 2 from the top. And I think that's it. The top's, nothing's going to factor. We can't get 17. That's a prime number. And that's just the way it is. To finish up, I have 2 other problems here. Part D would look like this. 6 minus 5 over k over 1 plus 5 over k. So there's 2 different approaches for this. One is we can get a common denominator on top, common denominator on the bottom. So we have one fraction on top, one on the bottom, and then multiply by the reciprocal. An easier way to do this is to multiply the top and bottom by the overall least common denominator. This is the way that I would recommend. So if you look at the top, obviously we have a k in the denominator. On the bottom we have a k in the denominator. So if we multiply the top and bottom by k, what we would get is we would get 6 times k minus, well, 5k over k. These would cancel, which was the idea. And divide that by k plus 5k over k. And these would cancel also. So the best answer would be 6k minus 5 over k plus 5. Another approach for this would be to get a common denominator on top. So I'd say maybe this is like method 1. We could also get a common denominator. So we can multiply, so let me see here, 6 minus 5 over k divided by 1 plus 5 over k. We could multiply the 6 by k over k, so the top can be combined to be 6k minus 5 over k. The bottom, we can multiply the 1 by k over k, so we get k plus 5 over k. And we have the top divided by the 1 fraction on the bottom, which we already talked about we can multiply by the reciprocal. Giving us 6k minus 5 over k plus 5. We get exactly the same thing. I think the first technique's a little bit easier. So we'll finish this up. I'll show you the last problem here. It looks like this. A over a plus 1 plus 1 over a divided by 1 over a plus 1 over a plus 1. Now again, we could do this either approach, but just in the interest of time, I think most of you would agree the first way was a little bit faster. It looks like the LCD across the top and the bottom for both would just be a times a plus 1. So what I'm going to do is I'm going to multiply the whole top by a times a plus 1. I'm going to multiply the whole bottom by a times a plus 1. And that should cancel out our fractions and give us the answer in the fastest way possible. So I'm going to go ahead and do that here. We have a times a plus 1 times a over a plus 1. This would be that. Plus a times a plus 1 times 1 over a. That's the whole top when we multiply by a times a plus 1. And then on the bottom, we're going to have a times a plus 1 times 1 over a. And then plus a times a plus 1 times 1 over a plus 1. When we multiply and divide by the same thing, they cancel. So these cancel. These cancel. So on top, we're just left with a times a plus a plus 1. That's all the top turns into. A squared, and then we have this. In the denominator, the a's cancel, and we have a plus 1. The a's plus 1's cancel, we just have a. So we're just left with a squared plus a plus 1 divided by 2a plus 1. And that's all it is. So if you could please take a look at the homework from this section, and let me know if you have any questions on Thursday.